this short video, we're going to go over how to use a table of common integrals, like the one shown here, which is found in the back of your Atkins textbook. And so I think it's most helpful to go over this by way of a couple of examples. The first example that we're going to do is one that we encountered in class today, where we were trying to find the integral from 0 to infinity of k times e to the negative kx dx in order to decide whether or not this integral was normalized. So let's go ahead and actually carry out that integral. When you're using this table of common integrals, you'll notice that there's a section of the table that's devoted to indefinite integrals when you don't have specific integration bounds, and then a section of the table that's devoted to definite integrals when you do know the integration bounds. We have integration bounds in this problem, so we're going to be using the right-hand side of the table. And what is really important when using this table of integrals is you need to be able to match something in this table to exactly be what you have in your integral expression. It's okay if there's different constants, but it's not okay if there's x's or k or e to the negative x's showing up that are different from what you're trying to solve for. So let's go ahead and look at our version of the table. And what we see is that, in fact, there is an integral that matches what we're looking for. And that integral I'm going to highlight in a red box. You'll notice that there's a couple integrals that are x times e to the negative kx, but only one integral that has e to the negative kx by itself. And so that's what we're going to use in this particular problem. So going and zooming in on this one a little bit so that we can see it well, let's go ahead and make substitutions so that our integral matches exactly. The first thing that I'm going to do is I'm going to take this k out of the integral expression just so you can see why it is that constants don't really matter, because I can always take it out of the expression, and now this piece, the integral itself, exactly matches what we see in Atkins. Noting that we need to make the substitutions, and remember that a from Atkins is equal to 0, our lower integration bound, and b is equal to infinity. And so now we can go ahead and just, Atkins has already done this integral for us, so we can just go ahead and write down, keeping our original k out in front, Atkins result, which tells us that we should write out 1 over k times e to the negative k times a, which is equal to 0, minus e to the negative k times infinity. So this result still looks a little bit hairy, but if we remember two rules about how exponents work, we can simplify this pretty dramatically. The first rule is that anything you have raised to a power is equal, raised to the power of 0 is equal to 1. So we can go ahead and simplify. Since e to the 0 equals 1, we can simplify this first part of the expression to just be equal to 1. The second thing to note is that exponentials, when it has a negative sign in front, they're called decaying exponentials. So you may remember that they go towards 0 as the expression gets really large. So e to the negative infinity, or rather the limit as e approaches negative infinity, that's equal to 0. So this is going to simplify pretty dramatically. And what we're left with is k times 1 over k, which is equal to 1. So now using Atkins, we've just done the math to prove that this integral simplifies and is in fact normalized since the result of the integral is equal to 1. Let's do one more example. Here we have in green an expression x cubed times e to the negative x squared dx, and we want to solve for what this integral is. Once again, we're going to look through Atkins to see if there's anything that matches. And since we have a negative x squared showing up in e to the negative x squared, it turns out that this section called Gaussian functions is going to be our best bet. Looking over the table, I can see that there's one result that does match very closely to what we're looking for. And the only thing that we have to know is that in this case, k from Atkins is equal to 5 from our integral that we're trying to solve. Otherwise, these integrals match perfectly, and so we can go ahead and simply compute. And so we're going to find for this expression that from the result from Atkins, Atkins says this integral is equal to negative 2 times k squared. And so we just need to plug in our result of k is equal to 5 And once we do the arithmetic, we'll find out that this integral is equal to 1 over 50. So hopefully that showed you a couple examples of how you can use this table of integrals to solve tricky integrals. I would encourage you anytime in physical chemistry that you see an integral that you don't know how to solve, that you consult Atkins to see if this integral shows up in the table. All right, see you in class.